In this video, I will explain various cross-validation methods. Okay, essentially cross-validation method we need because we want to estimate the test error, not training error. Training error we can estimate from training process naturally. So we use entire data for training and compute the loss or error at every step, and then choose the best one among many different possible approaches. That is fine. So when you just use training error, rifle is very simple. But we have to estimate test error because in reality test error is what we really want to minimize. So there is gap between test error and training error, which is called overfitting, and because of this, it is very difficult to choose the best model from training error. And that's why we have to learn cross-validation. So this overfitting is also related bias and variance trade-off, right? And bias comes from the model complexity. So as you use more simple model, the bias error will increase. And variance as well. As you use more complicated algorithm or model, the variance also will increase. So from this, we can understand this. To compute the training error and compute the test error. And from this gap, you can understand which part, bias or variance, is the most significant part for your current algorithm performance. When this value is high, you can think variance is the most important part. We have to deal with the variance issue to have better algorithm. When this value is small, which means bias is the most important part, so we have to deal with the bias error part to improve your algorithm performance. So essentially from this value, when this value is small, we have to increase. When this is small, you have to increase model complexity. Because the most part of your test error comes from the bias error part, and you have to increase the model complexity to decrease the bias error. When this value is huge, when the training error minus test error absolute value is huge, your test error comes from your test error comes from basically variance issue. And to reduce the variance, you have to decrease the model complexity so that your algorithm or your model has less variance error. That is design rule, very basic design rule for your machine learning process. And also, one another very important property between the training error and test error and bias and variance trade-off is as you collect more data, you can expect less variance. That is very natural consequences. As you collect more data, you can use more data points to train your model. So although your algorithm has a lot of parameters, if your training data point is a lot more than the number of parameters, then basically your parameter cannot memorize everything. So the algorithm have to learn some patterns inside your training data point, which make really learning process. So if you have a very huge variance issue, the most nice approach is collecting more data. But the problem is collecting more data usually incurs some cost issue. It is very difficult in practice. So that's why you have to very carefully control the model complexity to optimize your test error. See the training error and test error, see the difference. If the difference is small, then increase the model complexity because the small gap indicate high bias and small variance. If the gap is huge, then you have to decrease the model complexity because the huge gap between training error and test error indicate there is high variance. So to optimize your test error, you have to decrease the model complexity. Right. So in this sense, when you split your entire data point into two different parts, training and test, it is very important to decide the size of training data. How much portion of your entire data set should be used for your training process rather than test process. In our textbook, we simply use 1/2 of your entire data point as training and 1/2 of entire data as test. That is also possible approach, but very recently, nowadays, we very flexibly control the size of training data point. We usually use more data for training rather than test. Because as you use more training data point, you can get more accurate model and you can decrease the variance, test error variance. So from this perspective, we usually use more training data point compared to the test data point. But if you use too tiny test data set, it also has generates some issue because when you use very tiny data point, which naturally have some high variance issue. With some probability, the test error constructed with very special data point, very rare data point, then with a very biased or very skewed or very rare test data point, we cannot estimate the real test error. The estimated test error can be far from the real test error, so your estimation is not accurate at all. And with this inaccurate test error, you cannot choose the best model in practice. So you have to very carefully choose the size of training data set and the size of test data set. Okay. So our textbook introduced another approach. Instead of just simply splitting data set into two different parts like training data and test data, we can use some more smart approach, LOOCV, leave one out cost validation. Essentially, in this model, we use only one single data point as test and entire remaining data point as training. This is good, as I explained earlier. As we use more training data point, we can train your model more accurately. So this is very nice news in the sense of the training process. But again, if you use very tiny test data point, which naturally generates very high variance on your test error estimation. Okay, so with this simple one single learning, your test error estimation will be very bad. I don't recommend this single learn LOOCV. So, through LOOCV approach like this, do not learn single time, but learn n times. This is the first run. At the second run, we use the second data point as test and remaining n-1 data point as training. Third run, only third data point will be used as test and all the remaining data point will be used as training. So we can repeat this process until the last data point used as test and all the remaining first n-1 data point used as training. After n number of trials, after n number of training and test process, we have n different error value, right? So by simply averaging out all this n number of trial, we can understand the test error of your algorithm. This is LOOCV approach. So it looks very good, right? We use almost all data points for your training, and also we use almost all data points for your test as well. Because at every simulation, we use different data point and we repeat the simulation n times. We repeat the training and test process n different times. So we use almost every data point for your training and we use every data point for test. It looks very good. But the problem is too many computation. Every training process requires some training time. We need some computing time to find parameters. This is not very simple process. Well, if you use very simple linear regression and your training data point is tiny, then you can get the best parameter in a second. But if you have more difficult running process like recent deep learning with millions of training data points and millions of parameters, then the training process requires hours or even days. To learn LOOCV with such huge data set is simply not possible. It's not allowed in practice, right? So LOOCV is good, yeah, when your model is very simple and your data set is not so huge. Or your model is linear, or polynomial, then there is some closed form equation that can compute the LOOCV cross-validation value from your training data point directly. But this is very special case, and for more general models, we cannot compute the cross-validation from a closed form equation. So for this, I recommend to read our textbook, equation number 3.37. Then you can see some close form equation to understand the cross-validation. But this is a very special case. In general, we don't have such close form equation. We have to learn n different training and test process, which will make huge training time, which is not allowed in practice.